Hello everyone, welcome back. This is our last fluid mechanics video, and we've got a fun one for you today. We're going to be talking about wind turbines. Today we want to show that the maximum power obtainable from a turbine is equal to 8/27 times rho times the surface area of the wind turbine blades times the inlet velocity cubed. Okay, so on our wind turbine, I'll just draw a quick picture. Okay, we have our wind turbine here. We have our air going in, our air coming out, V1 and V2, and then the velocity of the air at the turbine blades, okay? The turbine blades have a surface area of S, and that's what we'll need for this video, okay? So let's go ahead and set up a momentum balance question for this problem, or a momentum balance equation for this problem, okay? So let's start with, let's talk about power first. I think that's the best place to start. Okay, so we have power, and if you remember, power is equal to force times velocity, okay? This comes from our physics. You have work is force times a distance, right? And if we have power as work per time, then we get force times velocity, okay? So what is this force here? Well, recall from our last video that this force is going to be equal to the mass flow times the inlet minus outlet velocity, and that's because mass is leaving the system it's going through it, right? Okay, so we can get this expression for power to be, I'm just gonna write it right here, power equals, we have mass flow times V1 minus V2 times V. Okay, this is our first expression for power. We also know power in terms of energy, right? Power in terms of energy is saying some kinetic energy in per mass minus some kinetic energy out per mass times our mass flow per time, right? That's also an expression for power. Well, what that comes out to be is 1/2 times, we'll factor out the 1/2, right? V1 squared minus V2 squared times mass flow. Okay. Now, we can take these two expressions for power and set them equal to each other. We get mass flow, V1 minus V2 V equals 1/2 V1 squared minus V2 squared times mass flow. This is going to have a lot of algebra in it. Okay, so let's go ahead and solve for this V, this velocity of the fluid at the turbine blade. We can cancel out mass flow, and we can also expand this, right? So we get V1 minus V2 times V is equal to 1/2 times, and then we can expand this to be V1 minus V2 times V1 plus V2. Okay, these cancel out, and we're left with V equals 1/2 times V1 plus V2. That shouldn't really come as a big surprise. This is just the average of the entrance and exit velocities, okay? But now we have an expression for it. Keep that in the back of your mind, and we're gonna go back to our first expression here for power. So we have power equals, I hope I'm not blocking the screen here for you, or the whiteboard. Power equals our V1 minus V2 times V times our mass flow rate. What is our mass flow rate? Well, for a turbine, our mass flow rate has to do with the surface area of the turbine blades times then the density of the blades and the velocity of the air going through the blades, okay? So we get a reformed equation for power now that is the following. V1 minus V2 times S for surface area times rho times v squared. Okay, now we're getting somewhere. Now we can input our expression for velocity that we just found a minute ago back into here. We obtain the following: v1 minus v2 times s rho, and then v squared. V squared becomes 1/4, and then v1 squared plus 2v1 v2 plus v2 squared. Okay, continuing with our algebra, I said it would be a lot here. We can distribute this term out to here. I'm going to rewrite down here. We have power equals, I'm going to take our s times rho over 4 out here. Then we have v1 times this whole expression yields us v1 cubed plus 2v1 squared v2 plus v1 v2 squared minus, now we have v2 v1 squared, right? Minus, oh, I missed a 2. Oh, no, I didn't work it. Minus 2 v1 v2 squared minus v2 cubed. Okay, let's see. We should be able to simplify some things here. So we have plus 2v1 squared v2 minus v, where is it? Did I miss a term? I may have missed a term. Give me 1 second. Oh, here we go. It's right here. I'm staring right at it. I just wrote it in the reverse order here. That's why it confused me. So we have 2v1 squared v2 minus v1 squared v2. So we can get rid of this, and that takes out the 2. And then here we have the same thing, but with v1 v2 squared. We can take this out and get rid of the 2. Okay, that looks right. We're left with s rho over 4, and then times v1 cubed plus v1 squared v2 minus v1 v2 squared minus v2 cubed. Okay, now we have an expression for power as shown here. The next thing we're going to do is a handy algebraic maneuver. We're going to factor out v1 cubed and see what happens. If we do that, we obtain s rho over 4 times v1 cubed. We're factoring that out. We get 1 plus v2 over v1, right, minus v2 squared over v1 squared minus v2 cubed over v1 cubed. Okay, what was the point of us doing this? Well, we can now set a ratio, r, that expresses the proportion between the exit velocity of the fluid and the entrance velocity of the fluid. And when we plug this back into our expression here, we get power equals s rho over 4 v1 cubed times 1 plus r minus r squared minus r cubed. Okay? What we want to do now is we want to show the maximum power obtainable. We want to optimize this ratio. Okay? So what we can do, how do you optimize something? You take the derivative and set it equal to 0. If we take the derivative of this with respect to r, this ratio, we get s rho over 4 times V1 cubed. We get 0 plus 1 minus 2r minus 3r squared. We can simply set this equal to 0, right? To maximize it, set the derivative equal to 0. And we can do that by factoring this expression. So it looks like we have, if we factor this, we would get 1 and 1 minus 3r plus r. Okay, so r. We just have to pick one of these factors to set equal to 0. Obviously, we can't have it as -1. They're not going to equal each other, so we have to gain some power, right? So we're going to take this one, and look at this. R equals 1/3. Okay, so the ratio V2 to V1 must equal 1/3. Well, what is the power we actually generate from this ratio? So what we can do is we take this and we plug it right back in to this expression. Okay, I'll continue that over here. We get power equals S rho over 4 times V1 cubed times 1 plus 1/3 minus 1/9 minus 1/27, right? It's as simple as that. Okay. Now, if we work these fractions out, get like denominators for all of them, I guess we can do that here. This becomes 27 27ths plus 1/3 of 27 is 9, so plus 9 27ths minus 1/9 of 27 is 3 27ths minus 1 27ths. Okay, and we get 27 plus 9 is 36, minus 3 is 33, minus 1 is 34 over 27. Okay, so I'm just going to rewrite this as 34 over 27. 34 over 27. But remember, we have to take 1/4 of that. 1/4 of 34, well, 1/2 is going to be 17. Uh-oh, did we do something wrong here? 27 plus 9 is 36. Minus 3 is 33, minus 1 is 32. 32 to 27ths, not 34. 32 27ths. 1/4 of 32 is 8. Okay, so we get power equals S times rho times V1 cubed times 8 over 27. Okay, and this is our final expression for the maximum power obtainable from a turbine. All right, so I think we've done it. Unfortunately, this is the very last fluid mechanics video I will be posting. Thank you all for joining me and being such loyal viewers over the last few videos. I hope to see you again shortly. We'll see ya.